Log on, tune in, find out. Another good idea from Cambridge.
On inverse methods in inverse obstacle scattering. Please visit it. Please.
Thank you very much, Matti, for the introduction and for the invitation. About a year ago, when I got the invitation to give a highlighted lecture at this event here, at this workshop, I have to admit that I didn't know what a highlighted lecture was. And I have to admit, I still don't know what a highlighted lecture is anyway. But at that time, I accepted the invitation with great pleasure because I thought whatever I do, it will give me a very good opportunity to attempt to get some young people interested in the area of inverse scattering, an area which I like very much. And I like it basically for two aspects. On one hand, it is beautiful and nice mathematics with lots of challenging open problems. And on the other hand, inverse scattering also has its applications in the mathematical modeling of techniques, imaging techniques, medical imaging, remote sensing, non-destructive evaluation, etc., etc. I have to admit that from these two motivations, the mathematics is the more important one for me, since I love mathematics. And in the spirit of this institution, today it will be only mathematics. And the outline, let's see whether this is working. Yeah. Okay, we first should kind of clarify what scattering theory is. Scattering theory is concerned with the effects that objects, obstacles, or inhomogeneities have on the propagation of waves. And from the huge amount of possibilities here, we make two restrictions today. I will only talk about time periodic waves, time harmonic waves. This is what we usually kind of picture waves as, the time harmonic case. And I will only talk about obstacles. You will have the opportunity to learn more about scattering of inhomogeneities through the 4 lectures by Andreas Kirsch tomorrow and on Thursday. Let's look at a model case where we have a plane wave traveling from left to the right, and the color code kind of models the amplitude or the phase of the wave, and it's a plane wave because the planes of the same amplitude, or here in this two-dimensional picture, the lines of the same amplitude are planes. And in this picture, I have already included the object that I will place into this propagating plane wave. And the way it is modeled is a perfect conductor. And this perfect conductor now gives rise to a scattered wave, and it is obvious that the sources of the scattered waves are lying on the boundary of the scatterer, and this scattered wave has to be added to the incident wave to make the total wave, and we see that the total wave actually vanishes on the boundary of the scattering object. And now we have two different type of problems. We can look at the so-called direct scattering problem, where we are given the incident field, the plane wave in this case, and the scatterer, its location and its shape. And the question is to find the scattered field or the total field, for example, in some distance away from the scatterer, for example, on this circle or on this sphere around the scatterer. And the inverse problem reverses the roles, and here we are given the incident field and some information on the scattered field. For example, we measure the scattered field all around this object, and from this information we want to find the position and the shape of the scatterer. So I will address this problem, and the outline of my lecture is I will first formulate the problem more concisely, and then we'll talk a little on uniqueness, on the question of identifiability. Do we have enough information to identify the scatterer by means of the data we have available? And then I will mainly talk about iterative solution methods, and if time permits, at the end I will spend another 5 minutes or so on a certain variant of iterative methods, decomposition methods. So we have to start with a wave equation, a classical wave equation with a constant speed of sound if you talk about acoustic waves, or speed of light if you talk about electromagnetic waves in a scalar modeling, and U is the velocity potential or a representative of the electric field. And time harmonic waves are have the time dependence factored out in a periodic way with a factor e to the minus I omega t, where omega is the frequency. And if you plug this into the wave equation, then you find immediately that the wave equation is equivalent to this reduced wave equation or Helmholtz equation, Laplacian u plus k squared u, which is now an equation only for the space-dependent part of the solution. And whereas this quantity has to be a real quantity, and that's why we take the real part of this equation, u is a complex valued function with which models the amplitude and the phase of the space dependent part of the wave motion. So we will be concerned with the Helmholtz equation with a positive wave number k. And obstacle scattering now just is we have some obstacle, we have an incident field. Usually this incident field in my talk will be a plane wave, which is given by e to the I k, the dot product between the vector x and a unit vector d, giving the propagation of the plane wave. And then we have a scattered wave due to the object, and the total field is obtained by superposing both together. And we need some more equations to describe this. The Helmholtz equation for the total field has to be satisfied outside. It's an exercise to show that the plane wave satisfies the Helmholtz equation. So we want some, it's a lecture, I think, so we need some exercise as we go along. And depending on the nature of the object, and if you think of acoustic waves, this models a so-called sound soft boundary condition. The velocity potential is proportional to the pressure, so the excess pressure on the boundary is zero. This characterizes a sound soft boundary condition. And if you think two-dimensional, my presentation will be mainly in 3 dimensions. It also models a perfect conductor. And we also need a boundary condition, so to say, at infinity, which is the Sommerfeld radiation condition. It states that this combination of the radial derivative and the potential itself decays faster than 1 over r as the distance to the origin goes to infinity. This Sommerfeld radiation condition physically means that the energy is outgoing, and mathematically it ensures uniqueness for this Dirichlet problem for the Helmholtz equation in the exterior domain. And this radiation condition also, as a result, implies that the scattered wave basically behaves like an outgoing spherical wave. Here, if you have in mind the time dependence factor e to the minus omega t, you see that the surfaces of constant phase are spheres. That's why it's called a spherical wave. But it has an amplitude factor coming along with it that depends only on the direction of the point you are sitting at far out, plus higher order terms. So the Sommerfeld radiation condition and this asymptotics are equivalent, and now we are ready to formulate the problem again. We are given the far field pattern. Okay, I should have told you that this amplitude factor is known as the far field pattern or the far field of the scattered wave, and it basically means we know or measure the scattered wave at large distances away from the object, all the way around the object, and from this we want to find the shape and the location of the scatterer. And this is a nonlinear problem because the solution to this Dirichlet problem depends in a nonlinear way on the boundary, and it's ill-posed because due to the regularity properties of elliptic equations, this is a very smooth function, so the forward map is a smoothing map, and smoothing maps in general are ill-posed. I've mentioned the applications already. And the first question that comes to mind is that of uniqueness or identifiability. And here we have a very classical result, the only classical result in inverse scattering. Namely, if we assume that we have 2 objects such that the far field pattern coincides for all incident direction. D is the direction of the incident field, and x hat is the observation direction. So we are deviating from the formulation I've given so far because the aim is actually to reconstruct the unknown object from one incident field only, but all observation directions. Now we are kind of more generous and give more data, a lot more data, and then indeed one can show that D1 is equal to D2. So the far field pattern coincidence for all incident and all observation direction uniquely determines the object. And I want to briefly go through that proof. The main ingredient of the proof is Rayleigh's lemma, which tells us if the far field pattern vanishes, then the corresponding radiating solution to the Helmholtz equation has to vanish everywhere. And this is a very strong theorem because it basically, what I've written down here, actually is the first term of an asymptotic expansion with respect to 1 over x. And then the theorem tells us if the first factor in this expansion is 0, all the other factors also have to vanish. And this is, for example, not true for the Helmholtz equation, because if you look at the fundamental solution of the Helmholtz equation, it decays like 1 over x. But differentiating it, you can create solutions which decay faster. This is not possible for the Helmholtz equation. So this is Rayleigh's lemma, and this is what we are going to use. The idea of Schiffer's proof is we assume that we have two different objects, D1 and D2, which give rise to the same far-field pattern. And then we look at the unbounded component of the complement of the union of D1 and D2. And Rayleigh's lemma then tells us that for all incident directions from the coincidence of the far fields, we have the coincidence of the scattered waves outside this object in this domain here. And then what we do, we look at this shaded domain. This shaded domain is fully outside the object D1, and therefore the total wave U1 is well defined in this shaded domain. It satisfies the Helmholtz equation there. And if we look at the boundary, we can look at this part of the boundary. This is part of the boundary of D1, and therefore U1 vanishes on there because of the boundary condition. Then if you look at this part of the boundary, it's part of boundary U2. So we know U2 vanishes on here, but on here we have U1 is equal to U2, and therefore in this shaded domain on all of the boundary we have U1 is equal to 0. That means U1 is an eigenfunction of the eigenvalue minus k squared of the Laplacian with Dirichlet boundary condition. And then what we can show is that the total waves for different incident directions are linearly independent. This is basically, this will happen more often, I think, due to the fact that the plane waves are linearly independent and these guys decay at infinity. So we have infinitely many eigenfunctions for the negative Laplacian, but this is a contradiction now because the eigenspace of the Laplacian is finite dimensional. This is basically due to the fact that the embedding from H10 in this shaded domain is into L2 is bounded. It's compact, sorry. And this is true no matter what the regularity of the boundary is. I didn't talk very much about my regularity assumptions, so let's kind of do this. I assume for this talk for most of the time that the boundary is Z2 smooth. Then I can work either in the space of classical solutions or in the weak solutions. It doesn't make any difference because of the regularity properties for elliptic equations. So D1 and D2 are C2 smooth, but this shaded domain given by the intersection can be have a very rough boundary, and therefore actually this idea of Schiffer applies only for the Dirichlet boundary condition. It cannot be extended to other boundary conditions. I've given this proof or outlined this proof for 3 reasons. Firstly, each lecture should at least contain 1 proof. So we have outlined the proof, and you can lean back now. There won't be any more proofs. The second observation about this is that this result was never published by Schiffer himself. It appears as a private communication in Lux and Phillips' book on scattering theory, 1976. Schiffer and Phillips were colleagues at that time at Stanford. And the second reason for giving you this proof is this would not happen today anymore in a time of permanent evaluation and the permanent chase for grants, etc. Nobody would want to give such an important and valuable result away as a private communication to one of his colleagues. And the third reason is it's important in the proof that you use the correct shaded domain. If you make a set theoretic notation, you first have to introduce D star and then take D1 away from the complement of D star. You also can use an incorrect domain for your proof. Namely, it's much easier to write down, to take away from D2 the intersection D1, D2, and then in the case if the complement is not connected, you get a hole in here and the proof doesn't work anymore because you cannot show that U1 is equal to U2. This is only true outside from Redich's theorem. And if you look in the way Schiffer's proof is written up in Lux and Phillips' book, you will find that they used the incorrect shady domain. And this gives me some relief if these eminent authors, Lux from the Cornell Institute and Phillips from Stanford, have errors in their book. I can tolerate the errors in my books much more easily. I've already indicated that the proof does not work for other boundary conditions, and I will not go into other boundary conditions, but I want to come back to the question of uniqueness. We have too much information. So there are uniqueness results available for one incident wave under additional geometric assumptions, namely Colton and Sleeman. This is another classic proof on a certain assumption on the size of the object related to the wave number. Then actually one far field is sufficient to determine the object. And this is basically Schiffer's proof in addition with the monotonicity of the eigenvalues with respect to the domain. Basically what we have here, pi is the smallest eigen value for the Laplacian for the unit ball, and it took 22 years to kind of make use of the fact that the first eigenvalue of the Laplacian is a simple eigenvalue, and since we have complex quantities, with what I did here, we have two eigenfunctions, and therefore we actually can use the second eigenvalue for this estimate, and this was done by Chinidis. Pi is the smallest zero of the Bessel function, of the spherical Bessel function J0, which is sine x over x, and 8.99 is twice times the smallest zero of the spherical Bessel function J0. We can have other geometric assumptions. For example, if we a priori know that the obstacle is a ball, then it's also possible to show that one incident field is sufficient. And since about 2003, whole industry started by proving uniqueness results for polyhedral scatterers. This is the only occasion where I deviate from the C2 assumption on my boundary. And if we have a polyhedral sound-soft obstacle, then this is also uniquely determined by the far-field pattern for one incident plane wave. And let's just only look at the simplest case, namely assume that we have a convex polyhedral and in the two-dimensional illustration a polygon. and assume that we have another one which gives rise to the same far field pattern for one incident field only. And then it is possible to find a boundary part of the second obstacle such that the plane or the line going through that part of the boundary at least tends to infinity on the half line. It could be a corner case here. And then we know on this we have u is equal to 0 because u is outside. We know from Rayleigh's lemma that the total fields must coincide. We know that u vanishes on here, and by analyticity, since we now are outside of the object D, then we know that on here u is analytic, so u must be 0 on the whole line. Here it extends both sides to infinity. If we pass to infinity, the scattered wave goes to 0, but the incident field is e to the I something, so it has modulus 1 and it doesn't go to 0. So we have a contradiction if we assume that we have two objects. The general case is more involved and would need more than the rest of this lecture. So I'll finish off with talking about uniqueness and leave as a homework for you to prove uniqueness for one wave without any geometric assumption. This is a long-standing open problem, and you should be able to solve it. Okay. The next question one might be tempted to ask is that of existence, but this is an inappropriate question to ask, because what it would amount to is you would have to characterize measured far field patterns. So they have to live in some function space, and it cannot be the space of analytic functions, etc., etc. But anyway, what you would want to do is you would want to characterize far field patterns that can be extended in a way that they vanish, that the corresponding total field vanishes on a closed surface. And this is what I think beyond the possibilities of mathematical analysis. The main task is we assume that we have data for which that are correct or perturbations of this, and what we want to do is we want to kind of design approximation methods that are stable. And there are basically two classes of methods available. There are iterative methods, and they reformulate the inverse problem as a nonlinear ill-post operator equation or as a least squares problem. And then they solve this by iteration methods, which have to take into account that the problem is ill-post. So you use regularized Newton-type iterations, Landweber iterations, or conjugate gradient methods. And the other methods are qualitative methods, and their principal idea is to develop a criterion, each method a different criterion, and these criterion in general are in terms of linear integral equations, ill-post linear integral equations, and at some stage these integral equations, either the operator or the right-hand side, contain a parameter point, and then in principle these integral equations, the behavior of this integral equation, solvability or not solvability, etc., decide on whether a point belongs to the scatterer or not. And examples for such qualitative methods are the linear sampling methods, the factorization method, and probe methods. I will confine myself to iterative methods, and in Andreas Kirsch's lectures you will kind of learn a lot on the very exciting development on the factorization method. the simplest idea for iterative methods is you interpret the inverse problem as an operator equation where F is the operator that for a fixed incident field takes the scatterer or the boundary of the scatterer into the far field pattern. And what we now have to do is the forward problem amounts to I know the boundary and I have to solve the forward problem to get u infinity. So I have to apply this operator. The inverse problem is I'm given this far field pattern as measured data and I have to solve this equation. And to do this, to make some analysis and eventually also to implement it, it is required to have some parameterization for the boundary. And for simplicity, I should say the whole approach is not confined to this case only. For simplicity, I assume that the boundary can be parameterized as a mapping taking the unit sphere onto the surface. So I always will work with this parameterization P, and then I can view F as a mapping taking C2 functions defined on the unit sphere with values in R3 representing the boundary into the far field pattern, also lives on S2 and has complex values, and the inverse problems now in this formulation reads find the boundary parameterization P such that f of P is u infinity. And we can just think of Newton's method as we kind of learned it in high school for the first time, met it in high school for the first time. It basically means we linearize f for the parameterization P plus Q by f of P plus a derivative taken at P in the direction Q plus terms that decay faster than linear. And then if we are given an approximation P for the boundary, instead of solving f plus Q is equal to u infinity, we solve this is equal to infinity and neglect this part. So we solve this linear equation for Q in order to get an update by adding it up to Q. And of course, since we are having a ill-posed problem in functional analytic terms, this means that the operator F is a compact operator. And since the derivatives, the Frege derivative is sitting here, of compact operators again are compact, the linearization inherits the ill-posedness of the original problem, therefore regularization is required. And for the Frege derivative, we have a theorem that characterizes the Frege derivative. So what is the Frege derivative doing? It is kind of comparing the far field pattern for a domain with a boundary surface parameterized by P and for the surface with parameterization P plus Q in this sense here. And then the derivative is a linear map from Q, taking Q again into a far field pattern. And this is a far field pattern again for the Helmholtz equation in the exterior of the original domain, satisfying the radiation condition. And the boundary condition for this VQ is a Dirichlet boundary condition, and the right-hand side is an inhomogeneous Dirichlet condition, is given in terms of the normal derivative of the total field. U is the total field for the original unperturbed domain with parameterization P, and this is multiplied by the dot product between the normal vector and the perturbation vector. And there is another little proof actually. So it's a proof by hand waving only, namely this is the boundary condition for the total field corresponding to the perturbed domain evaluated on the boundary. This vanishes. And we now do just a Taylor expansion, truncated at the first level. We have the original domain, the total field for the original domain evaluated on the boundary. But then we see the Q occurs here. It occurs as an indicator for the function, and it occurs as an evaluation. So we get this term, the derivative of u, in the direction q, which is what we are hunting for, evaluated on the boundary. We want the boundary condition for that. And this is just the term that comes from, we evaluate this not only on this point, but we evaluate it on here. That way we get this gradient coming in, and using that u vanishes on the boundary, we can write it this way, and out pops this. This is only proved by hand waving, because we have to make sure that this kind of expansion or this expansion is valid, and this can be done either by Hilbert space methods or also by using the boundary integral equation. And then if we do the Newton iteration, so we solve the linearized equation, for example, via Tychonoff regularization, since it's ill-posed. This has been going on for about 20 years with a lot of people contributing to reconstructions in 2 dimensions. And after the millennium, so to say, there are also some reconstruction in 3 dimensions available. There are some pros and some contrasts. The pros for this method, the advantages, it's from the concept. It's very simple, Newton's method. This always comes to mind if we have to solve a nonlinear problem. And the numerical experiments show that the reconstructions are very good and accurate. However, since within the procedure we have to evaluate f and we have to evaluate the derivatives, and this means in each iteration step for the actual boundary that we have achieved at this step, we have to solve the forward problem for evaluating f, and we have to also solve it a number of times for the derivative. The latter can be made simpler by using the adjoint problem, but it's still time consuming since we need an efficient forward solver. And as usual with the Newton method, we want to be close with our initial guess to the actual solution to have it converge. So these are constraints about the numerical implementation. And from a theoretical point of view, the convergence is not settled. What does it mean? We have to actually explain what we mean by convergence, because this is an ill-posed problem, and therefore the classical results of Kantorovich on the convergence of Newton iteration for well-posed problems does not apply. Actually, we do some regularization, and what we want is, in the regularization, let's think about Tychonoff regularization. We have firstly to design a rule on how to choose the regularization parameter depending on the iteration step. So this is one thing you have to do. And then with iteration methods for ill-posed problems, I think this is a very kind of, you have to keep in mind that if you iterate too long, then the data error will take over and you create numerical nonsense. So whenever you iteratively solve an inverse problem, you also have to have a stopping rule. You have to have a rule which tells you a posteriori by the results you have obtained when you have to stop the iteration. And then by convergence result, one has to understand something like if the data error goes to 0, so you make a theoretical experiment, you assume that you can do this experiment, let the data error go to 0. Then for the convergence result are such that you want to show that this is a regularization method. That means if the data error goes to 0, the solution you obtain by your procedure. The procedure consists in giving a rule for picking the regularization parameter depending on the iteration step, and tell the algorithm when to stop, that the results converge to the correct solution if the data error goes to 0. There are some theoretical results on this question in a Hilbert space setting, starting with work by Bakoshinsky, and the school in Linz has made contributions to that. But so far, nobody was able to either show that the assumptions in their theory apply to the inverse obstacle scattering problem, or more general to inverse boundary value problems, or find a counterexample. So this is a second homework assignment for you to resolve this open problem. What I want to do here is, in the remaining 20 minutes, I want to talk about a few attempts that have been made more recently. This is why the Revisited is part of the title of my talk, to do iterative methods at somewhat reduced costs as compared to applying the Newton iteration to the full boundary to far-field map. And we start from Huygens principle. Huygens principle expresses the scattered wave in terms of the secondary sources on the boundary. These are the sources we actually saw in the second movie coming out from the boundary. The term Huygens principle is from physics, representing the scattered wave in terms of the secondary sources, and it's just manipulating with Green's representation theorem for the incident and for the scattered wave, and adding this together. So this holds for all points x outside the scatterer, and if we pass to the far field, we obtain this far field for the observation direction. So this is basically the far field of this fundamental solution to the Helmholtz equation. And since this is our data, I call this equation as a data equation, and we have two unknowns in this equation. Namely, we don't know the normal derivative of the total field on the boundary, and we don't know the boundary itself. We also can kind of evaluate this on the boundary. On the boundary, US is minus UI. So we get that on the boundary we have this expression, and this is a second equation for these two unknowns, and I call it the field equation because it basically represents the field through the boundary condition. Actually, this is an equation, this is an integral equation of the first kind, which you obtain by a single layer approach for solving the forward problem, and we will make use of that in a minute. So basically what we have here now is we have two equations for two unknowns. We know the far-field pattern, and we know the incident wave, and we want to find the boundary, and we have, so to say, this as a dummy variable which we are not interested in, but which occurs in our two equations. And the equations are linear with respect to this dummy variable, but they are nonlinear with respect to the boundary. And what we want to do is we want to linearize with respect to the boundary. And in principle, we have three possibilities. We could kind of, if we have an approximation for the boundary available, we could start solving this equation for the density and then use the other equation to linearize with respect to the boundary, or vice versa, or we could simultaneously linearize both. So we have three possibilities for designing a iterative scheme, and we recall the boundary representation, and we parameterize these integral operators, which we have now in the same way as we parameterized the boundary to far-field map. And we just plug in the parameterization, so our operators now are all operators mapping S2 into S2, but they act on the density, this is this part, and they also act on the parameterization P. And they are linear, nonlinear with respect to P. And if J is the Jacobian of this mapping, if we set psi in this way, our equations, the data and the field equation, then take this form. And the first observation we make is now the derivatives of these operators are much simpler than the more complicated representation of the derivative of the boundary to far-field map, in the way that we just obtain them formally by differentiating the kernels of the integral operators with respect to the parameterization. This is trivial here, and it needs some work to be done with this respect because of the singularity, and they are linearization in the sense that I have L2 in the image space and C2 in the pre-image space. And now if we assume that k squared is not a Dirichlet eigenvalue of the negative Laplacian, then this operator A, which is basically the single layer potential operator, is a homeomorphism. So this is used for solving the forward problem. And then what we do is, as I already indicated, we solve the field equation for this approximate boundary presentation. So we get it by inverting this equation. It's possible. And then we keep this density fixed and linearize the data equation with respect to the boundary, and have a linear equation which we solve for Q in order to update P into Q plus P. And this has been suggested and implemented in 2 dimensions by Thomas Johansen and Brian Sleeman a couple of years ago. And you might ask, does it have any relation to the linearization of the boundary to data equation? And the answer is yes, it has some relation, because what we can do is we can represent the far field map as the far field of the density that we obtain by solving the singular equation. This is an explicit representation of the far field map under the assumption that we are not at an interior eigenvalue. And you see here the P occurs at 1. Oops. Where are we? This way. The P occurs at 1, 2, 3 locations, and you have to differentiate with a product or chain rule, whatever you want to call it. And what we see is the derivative consists of 3 terms, and this is the derivative that occurs in the linearization of the far field equation. So what we can state is the linearization of the data equation in the system of 2 equations corresponds to the Newton iteration for the original boundary to far field equation, with the Frechet derivative approximated only through the first term. So this is a relation between the 2. We also can think of simultaneous linearization of both equations, neglecting the fact that one of the equations is linear. And when we do this, we have the data equation. We also have the linearization with the perturbation of the psi of the density, and we differentiate also the field equation, and in the field equation we also have to differentiate the right-hand side. This term is popping in, and this has to be solved if we have a approximation for the parameterization and the density, then we solve this linear system, 2x2 system for the q and the chi, and update p plus q and psi plus chi. This has been suggested by Bill Rundell and myself for the Laplace equation, and then by Olya Ivanishin, a graduate student of mine, we together extended it to various situations for the Helmholtz equation. Again, the question, does it have anything to do with the boundary to far-field map? And indeed it has. Again, the assumption we had before. So we, for a parameterization P, we take the corresponding density coming from the linear field equation. And then we have the following equivalence. If Q satisfies this linearized boundary to data equation, so we have Q, and we define a chi by inverting again the first order equation with a different right-hand side. Then Q and chi satisfies a system of linear integral equations that I had on the previous slide, the linearized system of equations, and also vice versa. If we start from this, here we have a solution Q and chi, and then we throw the chi away, and we get with a with a Q a solution of this map. But this is linked to the fact that the density psi here is the correct density, sorry, getting tired. Linked to the fact that this is a correct equation, so then this shows that this is different from this, but that this in principle can also be used to do this iteration by solving this system and always throw away the chi we got somehow. But in each case, then we have to solve the psi, get the psi again. So we still have a third possibility. We can linearize the field equation. So this means, again, with the assumption on k, one can show that the far-field equation, the far-field operator is injective and has dense range, and hence regularization makes sense. So we solve the ill-post equation first for the density, and then keeping the density fixed. We solve this equation by linearization. We linearize it and update it. And this has not been implemented in the literature, but it is related to a method which I've developed with another student of mine, which is a hybrid decomposition method. And it basically approximates the differentiations involved in a different way. I briefly want to make a couple of comments on, okay, one more remark is the method depends on where we put the Jacobian in the parametrization. What I've presented so far is we incorporated the Jacobian from the surface integrals into the density and get this equation. But we also can do it other ways. We incorporate the Jacobian in the operators, and then the density is just a normal derivative on the boundary. And the numerical results indicate that this is a better way to do, and the motivation maybe, or a heuristic implementation is, okay, we need the derivatives of this with respect to p, and plugging in the Jacobian somehow makes this operator more sensitive towards changing the boundary. And the implementation is, I'll just talk about one possibility: linearize the data equation and so we have to solve this well-posed singular integral equation, and the way we have implemented it is using spectral quadrature rules going back to V0 with more recent results of Ganesh, Graham, and Sloan, and they are have a high approximation degree, so you can solve the three-dimensional problem using something like 150 or 200 integration points only. So this is reasonably fast. And then in the second step, we have to solve this ill-posed linearized data equation. It has a smooth integrand, so we can use Gauss trapezoidal rule. We are living on a sphere, but this ill-posedness requires some regularization. And what we do is, in the examples, we make we assume that the boundary is star-like and represented in this way, where the radial function is approximated in terms of spherical harmonics, and we collocate this equation at a number of points on the boundary, and not on the boundary, on the this must be the surface S2, and solve this system by penalized least square, penalized via Tikhonov regularization. And this is an example, though this is the original obstacle to reconstruct using something spherical harmonics up to degree 8, and starting the iterations with a unit ball, and you see how the iteration proceed, and after about 11 iterations we get a reasonable reconstruction. And a more complicated object, again starting the iterations with a ball, we get after 13 iterations satisfactory reconstructions. So I have a question. Do I have another 5 minutes? Okay. So I can briefly talk about decomposition method. It will last only for 5 minutes, I think. The basic idea of decomposition method is to decompose the inverse problem into a linear ill-posed part and a nonlinear part, to separate the two difficulties in the problem, the ill-posedness, which is a more severe difficulty, and the nonlinearity. Basically by first reconstructing the scattered field from the given far field pattern, which is difficult because we don't know what is the domain we have to kind of reconstruct the scattered field. And then in the second step, assuming that we have an approximation of the scattered field, we try to find the boundary by the location of the zeros, or more simply just by visualize the total field color-coded and see it from the visualization. And we have seen the fundamental solutions so far, but I have not introduced the notation. For the rest, it's a little bit better to kind of have a shorter notation for the fundamental solution. And the potential method basically what assumes that this is the obstacle that we want to reconstruct, and we assume that we have enough a priori knowledge so that we can place a surface in the interior, and we try to represent the scattered wave as a single layer potential on the surface with an unknown density, and then we can work out what is the far field pattern of this density. This occurred in the data equation already, and what we have to solve now, this is our far field pattern, and in order to find the density we have to solve this ill-posed equation, for example via Tikhonov regularization, and plug the phi back into here. Then we get that the scattered wave is given in this way. Here I've incorporated the Tikhonov regularization solution of this here for x in the interior of x. And this is a method that had been suggested and developed and implemented by Andreas Kirsch and myself some 25 years ago. So we revisited a lot of things here today. Another decomposition method is the point source method, which is slightly more complicated, but it starts with Green's representation theorem, and now we do it the other way around. We take the surface outside. So now we have a gamma sitting outside. And we can represent the scattered wave in this way. And what we then pass to the limit and work out this far-field pattern of this from this formula. And what we now do is we approximate the fundamental solution by this expression, and this is the so-called Hercules wave function. It's a solution, entire solution to the Helmholtz equation with this kernel, and we indicate the dependent on D on here. Assume that we can do this, then we plug this in here and reverse the order of integration, and then we have this equation as an equation for the scattered wave in terms of this kernel function of the Hercules wave function approximating the fundamental solution. This can be considered as a back projection formula. We project the far-field pattern back to this scattered wave. And quite interesting, through some miracle, this formula just is written on the blackboard in the male bathroom somehow. I don't know why. Anyway, how do we get this approximation for this? Yeah, what we try is we make the Hercules wave function to coincide with the fundamental solution on the surface. This gives us this integral equation with this Hercules kernel. I think the 1 over 4 pi should be 1 here. And we solve this via Tikhonov regularization. And again, if you plug this into the back projection formula, we get this coming in, and R is a reflection operator on the unit sphere. And this is Potthast's point source method. I've written both up again here, and you can compare these. And the interesting thing is they are identical. This is a result preliminary by Potthast and Schulz, and more recently by Liu and Potthast. They are dual in the sense, that they are, one is just a dual of the other. So, and this tells us, it gives us, if we take the same gamma, the same result somehow. This is what I find very interesting, and gives a new insight into the methods. And there are iterative variants of that, namely coming back to the data and the field equation. We solve the data equation, and we get the total field by this superposition. And then we find an update by linearizing the boundary condition, just by taking the gradient and solve this linear equation for Q. And this actually is equivalent to linearizing the field equation only with respect to the evaluation point. And this is what I've announced as the decomposition method Petro Serrano and I were working on. And one can do the same thing with the point source method, namely, okay, you solve, you assume you have a current. So we do this method interactively in a way. You solve the Hercules equation, and you get your approximation for the boundary, for the total field, and you find an update by exploiting the boundary condition. And this, in essence, is a method that had been suggested by Potthast more recently under the fancy name of a lasso method. I'm at the end. I'm advertising a book you might want for additional reading. I have 4 papers on the result I was kind of speeding through by my 2 graduate students and myself. And most of it is also contained in this handbook article that appeared recently. Thank you very much.